What's up, guys? Hope you're having a great day. Today we're going to be talking about Newton's laws. These are just some laws of physics that are really important, not only to physics, but to science as a whole. You might see them in chemistry to describe molecular motion, or in biology, or really any type of science. If you look deep enough, there's going to be some reference or some use of Newton's laws to explain some phenomenon. So these are very important laws, but they're a lot of times hard to understand because the language is technical, and it seems like they're using a lot more words than they really need to explain something, especially something that's really pretty simple, something that we a lot of times already know or have an idea about, but can't really describe in words. So that's what we're going to be doing today, is going over these and breaking them down and relating them to things that you can see, you can feel, and you can understand. So let's get started. Newton's first law is an object at rest tends to stay at rest, and an object in motion tends to stay in motion unless acted upon by an unbalanced external force. Now, this is also known as Newton's law of inertia, or it kind of just describes the behavior of massive bodies, or bodies that have mass. So it's just saying that if a mass is moving or not moving, whatever its state of motion is, it wants to keep that state of motion. It doesn't want to have to change, and it won't change unless something outside of it applies a force to it. Something outside of it touches it or pushes it or does something to it to make it change its state of motion. So that really all this is saying is that if you have a mass and it's moving or not moving, it's going to stay moving or not moving. Whatever it was doing, it's going to keep doing that until something else intervenes. So the second law is probably the most well-known and the most used, especially in Physics 1. The acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force in the same direction as the net force and inversely proportional to the mass of the object. So essentially all this is saying is it's spelling out for us force equals mass times acceleration, or that a force applied causes an acceleration, causes a mass to accelerate, which is kind of what we see up in Newton's first law, is that if we apply a force, then we can make something change its state of motion. And third, for every action, there is an equal and opposite reaction. Now, this is something that maybe we don't really understand too well, but if you think about it, it really makes sense. If I were to push on the car, maybe it seems like the car is pushing back harder, or maybe it seems like I'm pushing harder on the car because the car is not doing anything. But in actuality, I'm pushing on the car just as hard as the car is pushing on me, because we're in contact and we're applying that force. There's a Newton's third law force pair, as it's called, between us. So we'll go into that further later. So let's look at the first law. An object at rest tends to stay at rest, and an object in motion tends to stay in motion unless acted upon by an unbalanced external force. So, if this is kind of a little bit counterintuitive for what you think of when you see like maybe a baseball. So if I were to throw a baseball like this, if I were to throw a baseball, we would see its speed or its velocity to the right in this example. And by Newton's first law, we could say, okay, well, if it wants to stay in motion, in that same state of motion, then wouldn't it just continue on forever? But we don't see that happening in the world. We don't see if you throw a baseball, it doesn't go off into space. We know that it does slow down, it eventually falls, drops to the earth, and stops rolling. So how can we reconcile this with Newton's first law? Well, if we take into account all the forces that are acting, because it may not seem like anything is happening to the ball. It may seem just like, well, my hand applied a force to the ball, and that was it. There's nothing else happening. But in actuality, if we were to draw a free body diagram for this ball, we would actually see that the air resistance from the air is actually pulling backwards, opposing the motion, because all those air molecules that the ball is hitting are kind of slowing it down bit by bit. And it's not a lot, but over time it can really, really slow down the ball and eventually stop it. But also we have to take into account the gravity, the force of gravity, which is pulling straight down. So here we see that there are two forces, and after I release the ball, there isn't a forward force or an upward force on the ball, excluding very minor physical things. There really are only these two forces on that ball after it's released, after it enters ballistic motion. These are the only two forces acting on it. So it makes sense that even if it's traveling to the right, even if it's traveling this way, that eventually the force vector, the acceleration would be in this direction, would be pretty much towards the ground, and most likely the air resistance would be much smaller in magnitude compared to gravity. But in general, the acceleration, that ball is slowing down because of these two forces. That ball is slowing down and dropping to the ground, which is what we observe in nature. So this is how we kind of see how physical objects follow Newton's law. You have to break it down and see what are all the forces happening to this ball? What are all the forces happening to this object that would make it act like it does? So let's move on to the second law. And the acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force in the same direction as the net force, and inversely proportional to the mass of the object. So really all this is saying is that F, or force, equals the mass of an object times its acceleration. Or if you want to think about it this way, which is a lot of times more helpful if you're trying to solve a problem, if I apply a force, if I apply an unbalanced external force, then there will be an acceleration. An acceleration will occur on that mass. To keep this relationship true, that if a force is applied, then an acceleration, we will see an acceleration. Now, you can also flip this around in your mind and say, okay, well, if something is accelerating, there must be a net force on that object. And that a lot of times is useful for a physics problem, because sometimes they'll give you some example like in a certain part of space, a ball is accelerating to the right at 48 meters per second squared. So what is the draw a free body diagram for this object? And and if you want to keep this accurate, if you want to keep the forces accurate, you're going to have to show that there is an unbalanced net force to the right, because we see the acceleration is to the right. So I don't know what the exact free body diagram would look like, but we would see a large force over here. Maybe we would see a smaller force here. We could see canceling forces over here and here. But in essence, we would just know that everything here cancels to produce an acceleration or a force that is going to give us an acceleration to the right. So that's another good way to think about it if you're going to have to solve a problem where you're messing around with Newton's second law. So again, all it's saying is that if we apply a force, a net unbalanced force that isn't canceled out, the object will accelerate. And also, if we see an acceleration, there must be a net force on that object. And finally, for every action, there is an equal and opposite reaction. Now, this is something that is kind of hard to wrap your head around, so let's break it down, and let's stick with the ball example, and pardon my drawing skills because they're non-existent, but let me draw, let's say this is my hand, and I am just about to let go of this ball. I'm throwing it. I wound up and I'm just about to release it, but we're still in contact. So all Newton's third law is saying is that if we break it up, if we look at my hand and the ball separately, we would see that the ball is experiencing a force to the right from my hand, and that force on the ball from my hand is exactly the same in magnitude but opposite direction as the force from the ball on my hand. So these two objects, my hand and the ball, are exerting the exact same amount of force on each other, which may seem counterintuitive because if I'm throwing the ball, then I must be exerting a force, a bigger force on the ball because it's doing what I want it to do. It's going the direction that I want it to go. So that must mean that my hand is doing more work, it's exerting more force. But actually, they're exerting the exact same amount of force on each other. Now, because my hand maybe has more mass or my arm has more mass, then we know the acceleration isn't going to be as much. But we know that that force is exactly the same. Now, that doesn't mean that the ball experiences a force like this as well. It doesn't mean that on the same object we're going to see opposing and opposite forces. It just means that if we look at both of these objects, we're going to see we're going to see the action and the reaction pair, as it's called. And you can always know, if you see this in a physics problem, if you see, let's say, I'm pushing on a car, right, and they're asking you, what's the relative magnitudes of the force on the car from me, and what's the relative magnitude of the on me from the car? And you may have these ideas that maybe the car is pushing harder because it has more mass, and that is close. It's close. The car will accelerate less because it has more mass because of F equals ma, but it will experience the same force, just in the opposite direction. So again, that's really all it's saying, is that if you break it up, if you look at both the objects in contact with each other, then you're going to see the same magnitude of force, but just pushing back on each other. A pair of forces. So that's it. If you have any questions, please leave them in the comments. If you would like to see more videos, please subscribe and leave a like if this video was helpful. Thank you. Have a great day.